All right, welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell. You'll get notifications for this series and a bunch of other ones. This series is multivariable calculus. What we're doing is chapter 3, which is vector calculus. Specifically, 3.5 is curl and divergence. This time what we're going to do is the divergence of a three-dimensional vector field, and we're going to discuss the Laplacian operator because it's intimately connected to this process. All right, the divergence of a vector field is going to be, so we have a vector field over R3 again, and we have to assume a priori that the partials of p with respect to x, the partial of q with respect to y, and the partial of r with respect to z exist. If that's true, then we can define the divergence of that vector field as the del operator dot product this time with f. The curl is del cross f, and dot product luckily is a much, I hope you agree, is a much simpler binary operation to compute, and it is going to be this vector del dot product with our vector PQR, which gives us this definition. The divergence of a vector field is this expression, which of course is why we wanted these to exist in the first place. Let's give the interpretation of what divergence is actually doing. This terminology comes from fluid flow. If you have the flow of a fluid and then you have a point, so even if you, especially if you have, it's narrowing or something like this, and then you're going to look at this point, you're like, is this flowing faster than this one? This one's going to be faster probably, and then we describe that with a vector, and this magnitude will be longer because it's narrowing. So when we have a flow, what we now have is a fluid flowing in there, and when we pick a point, what we want is divergence is essentially telling us the net change at that point, or long story short, what the divergence is telling them is the tendency for that fluid to diverge from that point in your vector field. And that's why they call it divergence in general, mathematically. And if we get, and we're going to get a condition for when that happens, if div f is 0, then what that's going to say is, physicists call this that f is incompressible. And what that means is there is no divergence, there's no movement of the fluid in or out at that point. And then we're going to start talking about flux of fluid or stuff flowing across surfaces. And this is what Stokes and a divergence theorem are going to start talking about. And this is the machinery we're going to use, is curl and divergence. All right, I have a vector field. It's the same one we used in the curl example in the previous video. We have a vector field xzi, xyzj minus y squared k. We want to find the divergence of this vector field. Divergence of f is defined as the partial with respect to x of p. Remember, if you can't see it, I write it out for myself first. In this notation, this is PQR. So it will be this one, which is xz, plus the partial with respect to y of q x, y, z, plus the partial with respect to z of negative y squared. This one is going to give me z. This one is going to give me xz. And this will give me 0, and that says the divergence of f is equal to z plus xz, or x plus 1 times z, which coincidentally, as long as z is not 0 or x is not 0, we're going to get x is not negative 1. This is not 0. This vector field is compressible. Let's do one more. Divergence. Let f now be this vector field. Can you find conditions on a vector field such that its divergence will always be 0? Yes, I can. Can you? Once you're a wizard, you can. What I'm going to do now is the same thing. If you want and you forget the last one, I was lazy, but let's go back to the definition. I like to regurgitate all the way from the definition what div is. Divergence of f is by definition, technically, mathematically, del dot f, which is in symbols now. Del is always this operator, which is nice to remember. And then they change your function. It's this one. And then they usually give it as this stupid notation so that you have to turn it into this vector so that you know what you're doing. And then this is yz, xz, xy. Now I have two vectors, dot product. What is that? The sum of the coordinates, and then the multiplication technique, we're applying the operator to that guy. But this gives us the partial of x with respect to yz, a function entirely of y and z only, plus the partial with respect to y of a function of x and z only, and then plus the partial with respect to z of a function of x and y only, which is 0 plus 0 plus 0, which is by associativity 0 plus 0, which is 0. Therefore, if you have a function where p is a function of only y and z, and q is a function of only x and z, and r is only a function of x and y, div will always be 0. This is incompressible in physics terminology. Okay, we have an analogous theorem for divergence of curl of f, like we did in our previous video for curl. If we have a vector field over R3, we're reverse engineering this for what's about to happen in the proof, but if p and q and r have continuous second order partial derivatives, and then I can use Clairaut's theorem, then divergence of curl of f is 0. I can start trying to map out where I'm going. Clairaut's theorem got a name, and then I use mixed partials all the time, and that seems to be how I'm going to show this, and then I'm going to get curl, and remember what curl is going to do. What is this expression going to look like? That's del dot product del cross f. Let's look at that. Proof. Div of curl, which is a vector add, is equal to del dot product with del cross f, and that is equal to this guy, the partial x, the partial y, the partial z, dot product with now which hot mess? I, j, k, the partial with respect to x, the partial with respect to y, the partial with respect to z of p, q, r. Then curl is the cross product of these two, so this is the curl. So what is that going to give me? When I block off this one, I'm going to get the partial of r with respect to y minus the partial of q with respect to z, comma. Then I'm going to block off this one. So, and then we're going to get negative. So we're going to get the partial of, what am I blocking off? This one. So the partial of p with respect to z minus the partial of r with respect to x, and then the last one is the Green's theorem, the partial of q with respect to x minus the partial of, oh, we need a bigger board, p with respect to y. That's curl. This is del. This is curl f. What does that give me now? That gives me, way over here, the partial of x with respect to the partial r, the partial y minus the partial q, the partial z, plus the partial with respect to y of this coordinate, which is the partial p, the partial z minus the partial r, partial x, plus the partial with respect to z of the partial of q with respect to x minus the partial of p with respect to y. Now let's apply that. It's a linear operator, so we can distribute it across all of these, and I'm going to get what? 0, 0. d squared r dx dy minus d squared q dx dz plus d squared p dy dz minus d squared r dy dx plus d squared q dz dx minus d squared p dz dy. Now if you look by Clairaut's, the r ones, these by Clairaut's mixed partials are equal. I tell you so that I didn't just guess. I'm using Clairaut's theorem. Then I have q's. Z and x, x and z, those are equal by Clairaut's. Get out of here, I don't need you. And then triangle p, mixed partials, those are 0 equals 0, QED. Let's do one more thing involving divergence. Example 3, which is the same vector field as example 1, we found that it was compressible, which meant what? I'm not going to do it again. So del dot f, okay, which is divergence, if that's what the physicists want to call it. Del dot f is equal to, we saw, z plus xz, which is markedly not 0. Now what I'm going to do is use reductio ad absurdum to show that there cannot be any other function g, vector field g, such that the curl of g is f. Proposition: there is no vector field G of x, y, z such that the curl of G is equal to F. Can you see why? Now I'm going to use reductio ad absurdum, or RAA, which is, why didn't you just say it in English? Because it's cooler in Latin. Proof by contradiction. You don't want to have a political debate with Zeno. Watch some videos on the history of this. The technique is going to be, I'm going to assume that there is one and get a logical contradiction which will contradict theorem 1 immediately. Proof. Assume, on the contrary, that this F has G of x, y, z with curl of G equals F. Then immediately by our theorem, we have that the divergence of F is equal to the divergence of the curl of G, which is 0 by our theorem. But our divergence is not 0. So that says the divergence of F is not 0 and the divergence of F is 0. This is a contradiction. Therefore, we proved the fact that if you have a function whose divergence is non-zero, there is no other vector field whose curl is F. James Clerk Maxwell's equation starts talking about one vector field being the curl of another vector field and vice versa. In physics, we start talking about, so what that says is if your divergence is not 0, there is no other G. G doesn't exist. There cannot be any other function. And we use reductio ad absurdum to do that. Now let's do the Laplacian operator. All right, the Laplacian operator. Using this idea of del dot product of vector fields, we now ask ourselves, what if I have a conservative one, or where it's a gradient of somebody? So take a function of 3 variables. From that, create the vector function, the gradient. Then if I take the divergence of a gradient now, what's that? The curl of gradient is 0. The divergence of curl is 0. The first one's a 0 vector, the second one's a 0 number. This one now is going to be a dot product, so it has to be a number again, but it's a scalar. What is it going to be? The divergence of a gradient is del dot del f, which is going to be what we call del squared f. Or, long story short, the divergence is the second order derivatives of f with respect to x and y and z, and then we add those together. And then if we set div of a gradient equal to 0, this is what we call Pierre-Simon Laplace's equation. Basically, he was doing all kinds of stuff in physics and these types of things. And so there's 3 main forms of partial differential equations. The heat or diffusion equation, which has a specific form. The wave equation, which is waves of everything from water to Schrodinger's quantum mechanics. It's all the same form of equation, horrible PDEs. Or other things in physics will be described as the Laplace equation. It's the 3rd form of the 3 major types of partial differential equations, the Laplace equation. Please subscribe right here. Hit the notification bell below. I'll see you next time. Virtual drop.